Hello, this is Chuan Lei. Today I will present medical entity disambiguation using graph neural networks. This work is done in collaboration with Alina, Vasilis, Xiao, and Fatma. Medical knowledge bases or ontologies created from biomedical literature are expected to provide high-quality information to facilitate clinical decision-making. Tremendous effort has been put into developing automated medical knowledge base construction and completion. One major challenge all systems facing is entity disambiguation, namely how to map entity mentions in text snippet from medical source documents to their corresponding entities in the medical knowledge base. Text snippets in healthcare data are often collected from heterogeneous data sources. Editorial staff often refer to a medical entity in these data sources using acronyms or abbreviations. They may also introduce typos or colloquial terms. As a result, text snippet may deviate significantly from the canonical description of the entities in the knowledge base that they refer to. For example, an editorial staff member may mention ARF in a text snippet with the intention to refer to the entity that is defined as acute renal failure in the knowledge base. However, ARF can be resolved to acute rheumatic fever in the knowledge base as well. Such discrepancies make it difficult to link textual entity mentions to intended entities in the knowledge base, introducing noise, duplicates, and ambiguity, eventually decreasing the value of the knowledge base. The main challenge or challenges in entity disambiguation are the following. First, the semantic gap between a text snippet and the medical knowledge base can be huge due to the previously mentioned discrepancies. Second, we need a way to collectively learn contextual and structural information of entities in the text snippet. In other words, ambiguous terms in a text snippet should never be considered in isolation, as the surrounding words provide important context. Also, we need to leverage the knowledge base to connect the recognized entities in the text snippet. Such information provides more accurate semantics for the ambiguous term. Third, we need a way to capture discriminative contextual information of entities in the knowledge base. This is because not all neighbors of a concept in the medical knowledge base are equally important with respect to the ambiguous term. Some may provide critical contextual and structural information to disambiguate the entities in the text snippet. Also, using difficult or highly similar entity pairs from a medical knowledge base can further improve the capability of the disambiguation model. Here, let me briefly describe three representative graph neural networks used in our system. GraphSage is a seminal message pathing graph neural network which employs the general notion of aggregator functions for efficient generation of node embeddings. It leverages node features such as text descriptions, labels associated with nodes in order to learn the embedding function that generalizes to unseen nodes. By incorporating node features, GraphSage simultaneously learns the topological structure of each node's neighborhood, as well as the distribution of node features in the neighborhood. RGCN is a relation-aware graph convolutional network which handles K-hop message pathing over heterogeneous knowledge bases. Unlike GraphSage, that only considers the node-wise connectivity in the graph and ignores edge labels, such as the relations in knowledge bases, RGCN distinguishes different neighbors with relation-specific weight matrices. In the kth convolutional layer, each representation vector is updated by accumulating the vectors of neighboring nodes through a normalized sum. Intuitively, different edge types use different weights, and only edges of the same relation type are associated with the same weight. MAGNN is the state-of-the-art metapath-based GNN that supports heterogeneous knowledge base and learn subtle contextual structures in knowledge base using semantic-aware neighbor aggregations with composite relations. Intuitively, it captures the relative importance of different metapaths to nodes of certain type. By integrating multiple metapaths, MAGN can learn the comprehensive semantics ingrained in the heterogeneous knowledge base. All three graph neural networks are implemented using Deep Graph library on top of PyTorch. This makes our framework lightweight and easy to adapt to new knowledge bases, and other graph neural networks can be plugged into our architecture as well. Here I will describe the architecture of EDGN for medical entity disambiguation. The basic idea is to represent both a medical knowledge base and a given text snippet as heterogeneous graphs. Following the property graph model, we assume that nodes are associated with literal attributes in both graphs, where nodes and edges have different types. In a knowledge base, nodes correspond to medical entities and edges correspond to relationships between those entities. The entity mentions and extracted relations from the text snippets are represented as nodes and edges in the query graph. Medical knowledge graphs or knowledge bases are often curated and updated from text corpora in medical literature. The text snippets are also collected from these text corpora, so the neighboring structures of both graphs are expected to be similar. So inspired by CMS networks, EDGN uses two identical graph neural networks to generate the graph embeddings that encode all local structural information centered around the nodes in both graphs. These two graph neural networks share the same parameters and consume a node list and an edge list from both graphs. In a node list, each row contains a node ID, its attribute features, and its type. In an edge list, each row has a source node ID, a destination node ID, and the edge type. EDGN learns the representation of each node in the knowledge base based on its neighborings and the representation of the query concept with the question mark in the query graph. Such representation captures not only the node features, but also the topological structure of each node's neighborhood in both graphs. The matching module calculates their matching score, indicating the likelihood of two nodes matching each other. The matching module can be a multi-layer perceptron with one hidden layer, a log bilinear model, or simply a dot product. We optimize the model weights by minimizing the loss function through negative sampling. In our entity disambiguation scenario, a positive node pair consists of one node representing an ambiguous entity in the text snippet and its corresponding matching node in the knowledge base. And negative samples can be created by corrupting one node in the positive node pairs. To improve the disambiguation power, we introduced two optimization techniques. Our first optimization allows domain knowledge from the medical knowledge base to be injected into the query graph through processing the text snippet to emphasize critical information for entity disambiguation. This processing step includes augmenting entity mention and relationships during the query graph construction. Having entity mentions detected, we try to match them with the nodes in the medical knowledge base. For the matched entity mentions, we can infer their entity types based on their correspondence in the knowledge base. For example, we identify aspirin as an instance of drug, nausea as an instance of adverse effect. These identified entities and their types can help us disambiguate the remaining entity mentions, such as ARF, for which a match is not found. One can create a knowledge graph by a query graph by connecting each node pairs with an edge. Specifically, we try to construct the query graph to capture different relationships between a pair of entities, which provide critical contextual information to entity disambiguation. Here we Again, leverage the domain knowledge from the knowledge base to augment the query graph. An edge is added between a pair of nodes in the query graph if the knowledge base have their correspondence and there exists an edge between these two correspondence. Then the type of the newly added edge can be inferred from the corresponding edge in the knowledge base. For example, the nodes aspirin and nausea are connected by an edge of type cos in the knowledge base. Then the newly added edge in the query graph is of type cos as well. Similarly, we can add the has relationships between nausea and other entities in the query graph. We further designed an effective negative sampling strategy, which provide EDGN with harder examples, resulting in more discriminative power for entity disambiguation. Intuitively, these negative examples are very close to the positive entity in the embedding space, either due to their lexical or structural features. So we generate them by utilizing two different sources of similarity evidence, which emphasize on both semantic and structural relatedness between positive and negative examples. First, difficult negative examples should be semantically similar to the positive entity in the knowledge base. For example, a positive node pair is MH and malignant hyperpyrexia, in which MH is the ambiguous entity mentioned in the query graph, and malignant hyperpyrexia is the labeled positive entity in the knowledge base. Then MH and malignant hyperthermia can be considered as a difficult negative example, since the semantic similarity between these two entities is very high. Second, difficult negative examples should also share many common neighbors with the positive entity in the knowledge base. Intuitively, two entities are similar if they're related to similar entities. So in this work, we choose the commonly used graph edit distance to compute the structural similarity of two entities in the knowledge base. Only the local neighborhood, namely one-hop neighbors of an entity, are considered in this graph edit distance, which substantially reduces the computational cost. Finally, we integrate the above two measures into a scoring function, where this sim SE is the cosine similarity between two entity embeddings, and sim sub ST is the normalized graph edit distance. The resulting similarity score is in the range of 0 to 1. We use 5 datasets from the medical domain to evaluate the performance of our method. MDX is a medical knowledge base consisting information about the drug, adverse effect, indications, findings, and etc. Mimic3 is a public dataset with over 40,000 anonymized patient health record. BioCDR contains 1,500 PubMed abstract annotated with mentions of chemicals and diseases. NCBI also has 700 PubMed abstracts annotated with diseases mentions and their corresponding concepts in MeSH. Lastly, SHARE has 433 anonymized clinical notes from earlier Mimic2 datasets annotated with disorder mentions. We evaluate our EDGN using GraphSage, RGCN, and MAGNN. We also compare EDGN with the state-of-the-art methods, including DeepMatcher, Normco, and NCEL. DeepMatcher is a supervised deep learning solution designed for entity resolution in a tabular setting. In our setting, an input to DeepMatcher is a tuple containing an ambiguous mention from a text snippet and an entity in the knowledge base. We train and evaluate DeepMatcher with positive and negative tuples. Although the structural information from text and snippet and knowledge bases are not available to DeepMatcher, we choose it as an exemplar recurrent neural network method focusing on matching entities. Normco uses a deep coherence model for disease entity normalization, which considers the semantics of the entity mentioned, and the topical coherence of the mentions within a text snippet. NCEL creates a graph for candidates of mentions and then apply GCN to improve the disambiguation by directly aggregating information from linked nodes. We measure the performance of all methods using precision, recall, and F1, which are typical metrics for the evaluation of the entity disambiguation task. The EDGN variants consistently outperform other solutions in terms of precision, recall, and F1 on all datasets. The best performing EDGN variant offers an average improvement of 7.3% in terms of F1 score compared to the other best performing solutions. To make an abolition study on EDGN, we evaluate the performance of our basic EDGN without two optimization techniques introduced earlier. We observed that the semantic-driven negative sampling improves the basic EDGN by 3.5% and 4.5% in terms of F1 score on Mimic3 and NCBI. Similarly, EDGN benefits more from the semantic-driven negative sampling strategy on MDX, which is over 6.4%. We also observed the query graph augmentation is more effective on BioCDR and shared datasets. The reason is that the additional semantic information from the augmented query graph is more representative when the knowledge base is simple. We also analyzed the result of EDGN with 1 to 4 graph layers on all 5 datasets. We observed that the optimal number of graph layers is 2 or 3. When EDGN uses more than 3 layers, its performance declines. Although more layers allowed EDGN to indirectly capture more distant neighborhood information by layer-to-layer propagation, such distant neighbors would introduce much noise and lead to more non-isomorphic neighborhood structure between the query graph and the knowledge base. In this particular case study, we employed GN Explainer to visualize the important contributions of nodes and edges in knowledge bases when finding the matching entities for ambiguous mention. GN Explainer highlight, in this case, 3 most important edges that contribute the most to match squamous cell carcinoma with carcinoma epidermoid by EDGN. These edges carry critical information from different types of neighboring nodes. This indicates that our EDGN can learn and leverage the most semantically and structurally meaningful information among different types of entities and relations for entity disambiguation. In conclusion, we model medical entity disambiguation as a graph matching problem in order to leverage graph neural networks with a simple architecture. We present EDGN, a medical entity disambiguation system, using a simple architecture to leverage these graph neural networks. We introduced 2 optimization techniques to further improve EDGN's disambiguation capability. We construct the query graph and augment it with domain knowledge from the medical knowledge base. This helps EDGN focus on the right structural information from the query graph for making the matching decision. We also designed an effective negative sampling strategy, which provides harder examples to improve the disambiguation capability. The experimental result on multiple real-world medical knowledge bases demonstrate that EDGN is effective and outperforms the state-of-the-art solutions. That's all. Thank you, and I'm happy to take questions.